And so we come to our trickiest problem of this set. This is actually a problem that's really in three parts. We've got a 75 kilogram ski jumper that's set at the top of a hill, and the hill is at 50 degrees to the horizontal. We've got friction here, a very low value of 0.05, and the ski jumper is clearly going to go down the hill and accelerate, so we've got to find that acceleration. What we've then got to do is apply two suvat problems. We've got to find the speed of the ski jumper at the bottom of the hill after our 50-meter length, and then, assuming that the speed doesn't change as it goes from the downhill to the kick, what happens as the ski jumper is projected through the air. And we're going to assume that there's no air resistance, and that the kick is 20 meters above the landing field. So like with all these problems, we have to start with the diagram. So let's bring our hill in, and it's at 50 degrees to the vertical, to the horizontal. We'll put our ski jumper on at the top of the hill, and let's consider the forces acting on it. Clearly he will have his weight as always, and our ramp will push off with the normal reaction force, and because there's friction involved, then there must be some sort of friction acting along the surface going backwards. So we'll label these mg, r and mu r. Now we've got our diagram, we can move on to doing the maths. So before we can solve this, we need to actually consider what is going on both parallel and perpendicular to the slope. So parallel, we have the parallel component of the weight minus the frictional force equals the mass times the acceleration down the hill. And then if we consider perpendicular to the slope, well, we can say that the reaction force minus the perpendicular component of the weight force equals 0. The ski jumper is, after all, not sinking into or floating off the hill. So what we can now do is we can combine those two together by substituting for r to get this equation. And first of all, you should notice that there's a common factor of m, so the mass of the ski jumper actually is irrelevant, and we can therefore simplify this slightly and substitute some numbers, and we get this arrangement here. So g brackets sine 50 minus mu cos 50 is our acceleration. Plugging the numbers in, trusting our calculator, and we find that the acceleration parallel to the slope is 7.199 meters per second squared down the slope. Now that we have our acceleration, we can attempt to do our first suvat, and this time we're going to just work parallel to the surface. So if we bring in our data table, the ski jumper is going to travel 50 meters down the hill, starting at rest. We don't know what the final velocity is, that's what we need to find out, but we do know now that the acceleration is 7.199 meters per second squared. So we need an equation which doesn't have t in it, because we don't care about t, and the only one we've got to use is v squared equals u squared plus 2as. Now if we rearrange this for v and substitute the numbers at the same time, we get this equation here. I've left the zero in here for clarity. So v is the square root of 2 times 7.199 times 50, which turns out to be 26.832 meters per second. So at the bottom of our run, our ski jumper is going at 26.832 meters per second. Now that we know how fast our ski jumper is going, we can bring in our data tables for the projectile part of the motion. And we have vertically a drop of 20 meters, the field is 20 meters below the kick, and an upwards velocity. We're going to assume the kick pushes the ski jumper upwards, 26.832 sine 15 degrees. We don't know what the velocity is, we don't know what the time is, but at least we know that the acceleration downwards is g, so minus 9.81 meters per second squared. If we consider the horizontal as well, this point. Again, we don't know S, but we know that's going to be the range. We can assume there's no air resistance, so A equals 0, and our U is our horizontal component of our velocity, so 26.832 cos 15. Clearly here, the thing which is going to link these two is the time. So we're going to work vertically to start with, and we need an equation to find time. So we're going to bring in our favourite equation, which is S equals ut plus a half at squared. Now, we're going to do a lot here in the next step. We're going to substitute all the numbers, and we're going to bring all the right-hand side to the left. So we're going to end up with an equation that looks like this. 4.905 t squared, so that's half of a, and it's become positive because we've moved it to the left, minus whatever's in that bracket is our u, and again it's negative because we've brought it to the other side, minus 20 equals 0. Now, I have no desire to solve this quadratic, so I will use a quadratic solver to do it, and it gives us two answers, of course, negative 1.432 seconds, or positive 2.848. Clearly here, only the positive actually makes sense. So now that we have our time, we can consider just the horizontal component, and obviously we're going to use only the positive value of time here, otherwise it wouldn't make sense in the physics world. And as we've got to find S, we're going to bring in our favourite equation again, S equals ut plus a half at squared. Now the rightmost part here is going to be equal to 0 because A equals 0, which means although it looks mean, it's just simple numbers. Our range is going to be 26.832 cos 15, all multiplied by 2.48. And this should give us a range of 73.81 meters. This is the end of the problem. A long way to get there, lots of different steps, but if you can follow this, you should be able to do any problems involving Newton's laws and suvat.